Hey, welcome back to our series on building a sort of 8-bit virtual console with lots of AI. As you can see from the screen, I have sprites working. So I've added the sprite system and created a simple assembly program that demonstrates their usage. And I thought I'd take a different tack in this video to previous ones, which is just to kind of work backwards from the work that's been completed. The reason for that is there was quite a lot of work to do this. But also, it feels like it's getting a little bit redundant watching me type something into Claude and then have Claude do it and then me tinker with code. So I figured it would probably be a point where it's more interesting to show what the console can do and backtrack from there. But as you can see, it's animating sprites quite happily with transparency in them. The colours shift halfway down because if you recall, we've done scanline palette selection. So each scanline can actually have a different palette. And I configured this demo so that halfway down the screen we'd switch palettes to demonstrate that works and prove to me that that works. And yeah, so I won't walk through all the code, but this is obviously been added to the source code. There is a sample project that just demonstrates, just does this. It's not too complicated actually because we're no longer having to worry about writing the exact bits to the screen. We're really just saying move the sprite positions. Because we haven't got that many sprites, we're doing all the movements in the VBank, we're doing calculations in the VBank handler. If we had a more complex game, we'd probably be calculating things outside the VBank handler and updating the sprite indexes in the VBank handler. But this is pretty simple. So we've got 6 sprites. I guess just to talk through how I got here, it's probably worth just walking back a little bit. If you remember, we added a sprite editor. And we added a palette editor, which is where the sprites of the palette are coming from. And then we added a cartridge bundler. If I just get the Solution Explorer up, we added a cartridge bundler too. That's the ROM file. I want the JSON file. Which lets us bundle things together. So that was the starting point for the work. The first thing I had to add was bank switching and getting the cartridge ROM not loaded into memory, but accessible by the CPU. So I had to have a memory space that the various components of the system could access. I mean, actually, the CPU isn't accessing the sprites. On a console, that would be a dedicated chip. And in our world, it's the renderer. If you recall, we've got this web GPU renderer, and that's been extended out to incorporate sprites and the shader. I guess the most important thing is we essentially put 2 things into the shader now, a sprite overlay and a frame buffer. So a frame buffer is our linear frame buffer. We can still write to the linear frame buffer, and our sprites appear over the top of the linear frame buffer. So basically, if we find a sprite pixel in our overlay, we write that. If we find there isn't one, we write the frame buffer. And in our sprite spec, I think we talked about it when doing palettes, index 0, the color index 0 in the sprite is always transparent, which is why we get the nice transparency. So we get the transparency. You can just see it sometimes when they go over each other. We get top left, there you go, there's nice transparency. So that's how that works. The sprites themselves are composed, oh goodness, I'm just now thinking, where is it? In a little sprite renderer. There it is. So this is similar to our linear frame buffer, but it's operating on the sprites. The sprites are in memory. It's not that exciting. I've got a little compile error. We don't actually use it in here. Okay, fine. Cool. I've not. I still need to do a bit of refactoring of some code in here, but I'm showing it pretty hot off the presses before I forget what I did. So that's that. Oh goodness, where's the console? Where's the console? Sort console. We've now got a sprite engine, so this is what interprets the memory. This is like our video chip essentially. Maps onto the sprite attributes from our sprite spec. I will show the spec in a moment. This is essentially our little sprite engine. walks through things, scan line and time. What I've not tested yet is the scan line limit. So I've tried to, obviously I've got infinite capacity on my machine for running an 8-bit console, but I'm trying to keep it true to 8-bit type hardware. So I've basically said if there's more than 8 sprites on a scan line, it can't display any more sprites, which is what was often the case on like a NES. A NES, for example, I didn't have a NES back in the day. I had a BBCB, but a NES, a Nintendo Entertainment System, had an 8 sprite per scan line limit, and it had a famous flickering when you started displaying more than 8 sprites on a scan line. And we can detect that. We set an overflow. There's an overflow memory space, so if we do get sprite overflow, the code can pick that up and go, okay, I want to adjust around it. I've not tested that yet. That would require more complicated assembly code. So we've got a sprite engine. Welcome to look at that. Obviously, it's all on GitHub. I just need to commit a couple of tiny changes, but it's all on GitHub. Quite a big change, a sort of painful change, was the introduction of bank memory. So it wasn't that painful. I'll show the spec for it in a minute. But previously we just had our 64K linear frame buffer, but now we need the different banks. So the sprites are on the cartridge, and we need to be able to tell the sprite engine what bank of memory on the cartridge the sprites are in. So I need to load that up. And the way I've arranged it, if we look at that spec now, I hope is fairly flexible, so we can do some fun things later on. This is the spec for the banking, for bank switching. Implementation specs might be more interesting. Here we go. Yes, right. I got a little diagram. I got Claude to draw me a little ASCII diagram. So the way I've arranged it essentially is we've got the lower memory, which is a 32K at the bottom. That's what we've always got. We've got bank 0. That's our frame buffer. Bank 1, 2 and 3 are just general RAM. And then the cartridge banks, the things we load into our cartridge bundler, are loaded in from bank 16 onwards. I don't think I'm going to put any more RAM banks in here. That would seem excessive for 8-bit hardware. We've got 128K RAM. That's pretty top end for a bit of an 8-bit hardware. So I'm not going to put any more RAM in here. But that's essentially how it's structured. So when you say and if you look at the sprite code, actually, if we just go into the console again, if you look at the sprite code, you will find sprite bank. Where is the sprite? It's in the intro. Here we go. Hang on. Here we go. Sprite bank. Right. So the cartridge bank is bank 2. We should have the cartridge open. So the cartridge, the sprites are in bank 2, but in our assembly, because the actual cartridges start at bank 16, bank 2 is actually bank 18 to the system. So just something to bear in mind when you're writing code, the first 16 banks are essentially reserved, 4 banks of RAM, a bunch of reserved banks, and then the cartridge banks start, which means the cartridge can only have 256 minus 16 banks, 240 banks. But that'd be a lot of ROM. But the nice thing about doing it the way, I say nice. Yes, I'm so smart. The nice thing about how I've done it, the reason I did it this way, the nice thing about doing it this way, is that we can actually point the sprite engine at a RAM bank. So we could actually generate sprites at runtime. We could use procedural generation to generate some sprites at runtime. We could copy sprites from a cartridge into RAM and then modify them. So I've kept it flexible. There isn't a rule that sprites have to come from ROM, they just have to come from a bank. So there's a little bit of work to get that in place. So that was stage 1. I needed to be able to do that. And then the next thing I did actually was just a little bit of sort of convenience work. Just to be clear, this is the spec I asked. So this is the spec I had for bank switching, which I basically worked on with Claude. It was fairly easy to say to Claude, this is what I want, can you give me a spec that I can use to implement? And I made some references to classic systems. So I wrote this with Claude. I think I used a website version of Claude to do this. I dumped in my sprite spec, I dumped in my memory spec, and I said, this is how I want banking to work. The questions it asked me were things like, are you sure you want to reserve 16 banks? That's quite a lot. And I was like, yes, because it's nice if it's 16 aligned and things like that. So we went through some back and forth. I asked it to, we made a few tweaks to the spec, but essentially it loaded this for me. Yes, but the thing I was about to mention, in the cartridge bundling, after I'd done the bank switching, I'm hopping around, sorry. After I'd written this, I asked Claude to, because this was quite a scary piece of work, I asked it to generate me a bank switching spec. And actually it did, when I reviewed the spec the first time around, it had done something which I really didn't want. It had decided that, and I hadn't been clear, I had to, from this, generate me from this in the code, generate me an implementation spec. And it generated me something that was somewhat like this. But what it had actually done is in the bank memory, rather than use a shared array buffer for the memory space and the cartridge space, it had decided that the cartridge ROM, those banks should be in the worker thread. If you recall, our CPU runs in a web worker, and that means we have to use messages to talk backwards and forwards, or a shared array buffer. It decided to use actual arrays, uint8 arrays, inside the worker thread, and use messages to access those arrays. But our web GPU renderer runs not in a worker, it runs in our system's main thread in the render loop, and it needs access to the same RAM. So when I reviewed the spec, I was like, oh, hang on 1 minute, this is not what I want, this isn't going to perform, let's rework this based on these criteria, and look at this, we need to integrate with that. And after we'd had that back and forth, we got this bank switching spec here, which was, again, I reviewed. It's interesting, obviously I'm taking a spec first, a sort of spec first approach to development with this. I'm finding, particularly as it goes on, I'm spending more time reviewing the specs than I am reviewing the code. That's partly because I think of time. I'm doing this in my spare time, and I kind of review the code over dinner and things like that if I'm not doing something else. And I work on these things, and these things I find if I get them right, they lead to much less downstream problems. So I literally went through this line by line, this spec, and spotted that and a few other things. I asked it to draw me this diagram, like I mentioned earlier, to clarify so that the spec would clear in the future. So bank switching. But I think then I said the next thing I went on to do was in our console we were, and I realised this because I ran something and I got a very strange screen. So I asked it to draw a sprite, and I couldn't see anything basically, or I think I saw like just white, or can't quite remember, but it was very odd. Sorry, my dog was probably jumping a mile. She's barking at the door. Somebody walking within 100 metres of the house. You probably can't hear, so I want to continue. Nobody can hear at work when I'm on Teams call, so I guess you can't hear. I'll continue. Goodness me, what was I thinking about? She's completely lost my train of thought. Yes, I realised that I had no palettes loaded. And the palettes were all pointing to index 0 by default when memory is zeroed. But we're defining palettes. We've got a palette editor, and we can bundle them into our cartridge. So that's interesting. I probably want the palettes to be loaded when the system is boots up. So a little tweak I got the AI to do was to basically store the index of the first palette bank inside the metadata, because once the bundle's compiled, all we can see is a list. It's just blocks of 32k memory. It can't see this, as it were. So I got it to I got it to add the index of the first palette bank to the metadata. And then when we load the cartridge in, like you plug the cartridge in, you turn the console on. One of the things it does is it takes that bank, if it exists, and it loads it into the palette space in memory, so that your predefined palettes, first batch of them anyway. You may have more than one batch, but the first batch of them will be loaded into memory, and you're good to go. I'm thinking about. I don't think many systems at the time really had like speedy mem copy built into the hardware as such. But it would obviously be nice to be able to copy those things in the future without having to write lots of complicated code. I could write a little, bit of assembly library to, let you load additional palettes in, or maybe we do something that lets you, move memory easily. Need to think about that. Adding like a fast memory copier probably takes it away from its 8-bit ethos, more into sort of 16 and 32-bit space. So I'm somewhat reticent to, but I'll see. This is supposed to be fun to work with, not just it's supposed to be fun to work with. In any case, I did that, and when I'd done that, that's when I got it to implement the sprite system. So I had my sprite spec. I think we took a very quick look at it in a previous episode. So I had a sprite spec. I'd obviously added this banking stuff, so I basically got it to create an implementation spec from the sprite spec and the source code and the memory layout spec, and look at the spec, look at the source code, create me an implementation spec, and it created me this spec. I reviewed this line by line again. I don't recall seeing any giant bloopers in it this time around. It seemed quite sensible. Nothing. Oh, excuse me. Nothing stands out to me, sort of in retrospect, as being as going wrong in terms of its generation of the spec. Just one thing. I actually just want to clarify just one thing. It had written somewhere that the sprite bank had to be from the cartridge. Yeah, this. It said that it had to be from the cartridge, and I was like, no, I don't want it just from the cartridge. It can be any bank. That was a very kind of oddball thing in here. And from that, it generated the code. We've just been looking at the sprite engine and stuff. Which is pretty cool. And I ended up here. I got my first test was basically just put a sprite in the center of the screen. When I made one sprite move, and then I was like, oh, let's put another sprite on, and another sprite on, and another sprite on, and then I made the sort of scan line split, and it resulted in this sort of assembly file, which I've added to the examples folder and is accessible by the AI, so it can build on it. And if you want to use the chat assistant, I'll cover it in a future episode. But another thing I've done is I have actually updated the support for running the AI locally, and it actually does a pretty decent job of local assembly generation now. I use a technique called constrained decoding to force it to only generate valid assembly. Now, valid assembly is not necessarily meaningful assembly, but we can cover that. There's an article on my blog about how that works. It's quite interesting, but it let me get a local model like Quen to work pretty reliably. I've got a pretty decent Mac, and it's still not the speediest thing in the world, but it does work, and it doesn't cost me lots of AWS credits, AWS cash. The other option is you can also, particularly now that all those examples and specs are there, you can also use Claude Code to work on the assembly, and it's pretty decent at it. It's very decent at it, in fact, but it can't interact with the breakpoints in the system, so, pros and cons. That's what I've got to. I think it's quite interesting. Oh, it's slowing down because I've got the debugger running. There we go. I found things get a bit weird when the debuggers are running. But it might also be some sort of memory issue. Who knows? It was like it's just getting something slowing down. Who knows? It might need a little bit of work there to see what's happening. I don't think it's actually the code. I think it's to do with the render loop or something. Maybe something happening on my machine in the background. Who knows? I hope that's interesting. Next steps, I think for me, I'm interested in having a go at the level editor, the tilemap editor. I think if we've got tilemaps and we've got sprites, we can start to do interesting things. Unfortunately, I'm not much of an artist, so I might have to spend an evening kind of cribbing some sprites from from the 8-bit days, so we've got something to work with and create a gbin file rather, some sort of stock sprites, and I'll start to keep these folders as projects, example projects that people can load in GitHub. So this one I'll save. So the gbin's there, the pbin's there, the cartridge is there. I'll save it as an example project, so you can open it up in the IDE and work with it, and have a go of it yourselves. I hope that's interesting. I hope this new format seems okay to people. If there's anything really spicy that I think might be weird or challenging for the AI, I'll still perhaps consider filming that way around. But I felt like it was getting a bit samey, like watching me do the same code, same steps over and over with Claude. There's only so many times you can watch that and it stay interesting, I think. So I figured a little switch might be interesting. That's it. Thanks for watching, and see you in the next episode.